Okay, quiz 12.2, enthalpies of phase change and heating curves. So question 1 here. Solid paraffin wax has a specific heat of 2.5 joules per gram Kelvin. If 300 joules of heat are added to 15.25 grams of paraffin wax, how much will the temperature rise? This will use Q equal to MC delta T. And in this case, we know Q. Q is going to be 300.0 joules. What is the mass of the paraffin wax? That will be 15.25 grams. The specific heat is given as 2.5 joules per gram Kelvin. And delta T is what we're actually solving for. In this case, delta T is going to equal a positive 7.9 Kelvin, or 7.9 degrees Celsius, because when you're talking about a change in temperature, it doesn't matter if it's Kelvin or Celsius. Okay, question 2 also has to do with paraffin wax. It has a melting point of 37 degrees Celsius and an enthalpy of fusion of 210 joules per gram. How many joules of heat are required to melt 5.75 grams of paraffin wax? Here we're going to use Q is equal to M delta H. And I want to point out that you could also use Q is equal to N delta H if you knew the number of moles of paraffin wax and you had a molar enthalpy of fusion, then you would want to use the N delta H. But in this case, we're given a enthalpy of fusion per gram by mass, and so we'll use mass. That's just a lot easier. And so we want, in this case, to take the mass of paraffin wax, 5.75 grams, times its enthalpy of fusion of 210 joules per gram. Pardon me. We only get 2 sig figs here. It's 1200 joules. Okay, and then this next problem is not very difficult when you take it one step at a time. But looked at as a whole, it's quite a monster of a problem. So table 12.3 in your textbook gives the necessary values to answer this question. It gives your enthalpy of fusion, enthalpy of vaporization, and specific heat for water in all 3 different phases, liquid, solid, and gas. And so the question is, if we have 38 kilojoules of heat removed from a 10 gram sample of steam, which is water vapor, at 250 degrees Celsius, give the total energy for each of the steps labeled A through E on the cooling curve below, and give the final phase and temperature of the water. So let's look at this cooling curve. Oh, you know what? I'm going to have to just, there we go. So this is the cooling curve. You can see that we start at a high temperature, and then as heat is removed, we have region A where the temperature drops. This corresponds to the steam cooling down from 250 degrees Celsius to the condensation point of 100 degrees Celsius. Then B, we have a flat plateau. That is the time where there is a phase transition from steam to liquid water. And the temperature remains constant during that transformation. Then C, the temperature is again dropping, and so this is liquid water at the boiling point, 100 degrees Celsius, cooling down to the freezing point of 0 degrees Celsius. And then region D, the temperature remains flat as that liquid water undergoes a phase change to solid water. And then E is when the ice will drop in temperature from the freezing point 0 degrees Celsius to the excuse me, to the ending temperature, and we'll figure out what that is. Okay, so we'll just get rid of that PDF viewer altogether, and we're going to keep track of two things. It asks for the energy lost at each stage, and then it's also going to be useful to kind of keep track of the total amount of energy. And so we're starting with 38 kilojoules. That is the total amount of energy that will be lost over all 5 steps. And we're going to kind of keep a ledger here of how much energy is removed in each step and how much energy remains to be removed. And that's where we'll keep track of that. Okay, so for step A, we're cooling down the steam. That means we'll use Q is equal to mc delta T. What is the mass? That's 10.0 grams of water. And the specific heat for steam, if you look at your table, is 2.042 joules per gram degree Celsius. And how much did the temperature change? Well, we started at 250 degrees Celsius and dropped down to the boiling point of 100, and so that is a negative 150 degrees Celsius. And that comes to negative 3,063 joules, so we'll change that into kilojoules, negative 3.063 kilojoules. And so if I started with 38 kilojoules, by the end of the first step, there's 34.94. Is this right? 34.94 kilojoules remaining. Step B was a phase change. So here we'll just use Q is equal to m delta H. We could convert our 10 grams of water into moles and use the molar amounts. Well, let's just use the amount by mass that is in the table, in table 12.3, and it'll be much easier. So we have, again, 10.0 grams of water, and the enthalpy of vaporization for water is 2.26 joules per gram. We're not vaporizing, we're condensing, we're going the other direction, and so this is going to be negative 2.260 kilojoules per gram. And this gives us negative 22.6 kilojoules, a substantial amount of energy. And so 34.94 minus the 22.6, we're left with 12.34 kilojoules remaining. Step C, the cooling of the water, is again going to be mc delta T. So that's 10.0 grams. The specific heat for liquid water is 4.184 joules per gram degrees Celsius. And the temperature changes from the boiling point 100 down to the freezing point of 0. So that's negative 100 degrees Celsius. And that's going to end up equaling a negative. We got nice good round numbers, 10 and 100. So it's going to end up as 4.184 kilojoules, which leaves us 8.15 kilojoules in our ledger over there. Now D, the freezing of the water, we're going to use Q equals m delta H. We've got 10.0 grams of water. Delta H, this will be the enthalpy of fusion, which is, hold up, 334 joules per gram. We're freezing instead of melting, and so that's going to be a negative 334 joules per gram. And so the total energy change for the system during step D is a negative 3.34 kilojoules. That leaves us with 4.183 kilojoules. So step A, you lose this amount, 3 kilojoules. Step B, you lose 22 kilojoules. Step C, you lose 4.184 kilojoules. D, you lose 4.34 kilojoules. And then E, you're going to lose the remainder. All the remaining energy is lost in step E. And this is the cooling of the ice. And the question now becomes, what is the final temperature? So if I use Q equals mc delta T, in this case Q is going to be the negative 4,183 joules. That is the heat lost by the system. And that's going to equal 10.0 grams times the specific heat of ice, which is 2.087 joules per gram degrees Celsius, times delta T. Delta T is our unknown, and when we solve this, we get delta T equal to negative 200 degrees Celsius. So our ice started at 0, it dropped by 200 degrees Celsius, and so that is also the final temperature. It's a good deal of the way toward absolute 0 by the end. And that's it for quiz 12.2.